This is a set of slides having to do with solving physics problems, and there's a sort of general outline of what's going to happen here. It's one of the series of videos that I'm making having to do with physics, and it tries to look at the various reasons for why you have some difficulty in solving physics problems. It's more involved than you think, even though when you perhaps have it first, you run right through it. A lot of it has to do with your temperament, impatience primarily, and the idea of the importance of planning the solution of the problem, especially when you don't see the answer right away. Steps in planning involve the analysis and synthesis, and then the execution, as I'll discuss later on. One of the things that recently occurred to me was that rather than classifying the solutions by the subject, like a ramp and a mass on the ramp and that sort of thing, perhaps it's better to classify the solution by the form of the mathematical equations. And you still have to understand the ramp and the mass analysis, but then the actual synthesis of when you pull the equations together, it's perhaps useful to look at the kind of solution, of the equation form that you have, and I'll talk about that. And then I'll give you some advice on studying and taking tests. Okay? So, whenever I ask students, I did a little tutoring to find out what the real problem was here, they'll say, I understand the material, but I can't solve the problems. And that's not so unusual. The understanding of the material means that they understand the content of the material and the sort of general physical feel for it. But the difficulty comes about in setting up the problem. And once they set them up, the students say that you usually can solve the equations. That's not always the case, because oftentimes there is weakness in the skills of arithmetic and algebra and solving equations. So the real problem is setting up the solutions to the problems, and that means translating the text and the figures to the various equations. And the difficulty is that the problems are very concisely written, so you have to unwrap them to get to the answer, or to get the solution. This comes about, a lot of this, because you lack the procedural knowledge and the experience. It's more than just a listing of steps. I've got a list of 10 sort of steps, but it's more than just those. You have to actually understand how to use them, what the strategy might be, what your tactics would be, the techniques, and some various tips. And I'll give you some of that as we go through here. Some of the examples of the solution and the explanation of the problem is a text. In the text, the professor or the teaching assistant works the problem. They read it, and they start, and they bang down through it, and they finish without stopping or explaining any of the intermediate reasoning. Why was this example even in the text? What does it show? That sort of thing. So it's sort of, they start, a sort of miracle happens in their minds, and then it finishes. And the miracle, of course, is seeing these various steps, seeing in their mind these steps. You do the problem, you start, there's no inspiration, no miracle, and then you're floundering, and then, of course, you don't finish. Not in all cases, but in a lot of cases with these physics problems. So what happens when you read a problem? You either see what's wanted, and then you know how to solve the problem. You don't see what's wanted or how to solve the problem, and that's the reason for these videos. After thinking about the problem, there may be an insight or inspiration of seeing the solution that occurs in a flash. Of course, for a flash to occur, you've got to have your brain prepared to see the solution. And other than just recalling from memory, I'm trying to get looking at this thing at a little bit different level than just recalling the solutions to various problems that you may have studied. Of course, with enough preparation and insight, the solution is almost anticlimactic, and you just kind of plow through it. It requires generating a pertinent set of equations, combining them appropriately, and then executing the mathematical operations. And it's kind of interesting to think about when you break the problem solution down like that, that it's more involved than you may think when you just jump into it and bang through it. So your jump deficiencies or difficulties that you have are often because you lack any patience. And in the homework, you'll just look for a solved or a similar solved example in the text, and you'll copy it and all the rest of it. Of course, that's not so good on the exam. But oftentimes, you'll solve the important parts or steps in a problem in your head. Of course, that makes it difficult to check, And if you get lost in your solution path, then it's hard to recreate it and find out where you were. So, but a lot of the difficulty is effectively in these higher level skills of analyzing and synthesizing a solution and evaluating using trigonometry and algebra and, and solving equations. Those skills oftentimes are a bit weak. You may have done problems similar to what you're given, but actually doing them and having to have the integral aspect of the physics problem and these these word problems, it can be a bit tricky. So you go to the professor or the teaching assistant for help, and the first thing you get is, how much time do you spend on the problems? And that doesn't give you any particular insight from the text or the lectures. Or if they work the problems, again, they'll just sort of show you and work through the example. They won't tell you exactly why they did the particular steps. Now, another sort of obvious things is the fundamental difficulty is you're being taught by geeks. They spend a lot of time to learn the material, and they expect you to do so also. To beat the geeks, therefore, you have to become one. And that violates the premise of this video series. I'm trying to give you a larger, an overview of this material, such that you will be able to, with a little bit of effort, you'll be able to understand and solve these problems. One of the keys is planning backwards and working forward. This divides the solution into two parts. It's often said, people say, plan the work and then work the plan. And that's fine, that's just a kind of a reversal of the words and sort of a double meaning. But the difficulty with students is that they don't plan. They start, if there is a plan, they start their plan in the direction of execution of the plan, and they just work the thing right the way through. And that's counterintuitive. It's counterintuitive that planning is actually done best backwards. It's a synthesis of tasks as a plan, but again, planning of these various things is, of the synthesis, which is the collection of these tasks, is by analysis process. By analyzing backwards from the end or finished product. You don't have to do this if it's just a one-step problem, because it's pretty trivial. But in most cases, and certainly in courses beyond, STEM courses beyond freshman physics, they will become more involved. So you start at the finished answer, which is also a good clue in deciphering the problem. And you say, to get this answer, what is the preceding step? Well, it'll usually be an equation, it'll have to be an equation, that has that variable in the equation. And then when you solve that equation, you'll have the answer. Of course, then the question is, how did you get to that equation? Because it may have some unknowns. And further up, and again, I'll show you a diagram of this. Another problem is that the physics problems are stated in a very concise manner. And to solve the problem, you have to sort of unwrap this problem statement. Missing, even though it's important, it's the elephant in the room, is to identify the values before and after the states or the conditions, and to recognize that there is a before and after condition. And then if there is a process, what were the process conditions that hold during the problem statement from state 1 to state 2, for instance. For instance, an impact problem, explosion of a stationary firecracker. After the explosion, you give some vectors of the two particles of mass that's going out, and what's desired is the momentum of the third or the remaining particle. Okay? The key to this problem is recognizing that the explosion, before the explosion in state 0 or state 1, the center of gravity of the firecracker mass had a 0 momentum, and there was no outside force applied, and so therefore the CG and the momentum of the system remains stationary and at the origin that you've chosen. It's the best thing to do at state 2. Or the problem condition becomes between states 1 and 2, and the equation is as below at the bottom. The impulse is equal to 0, which is equal to the sum of the momentum after minus the sum of the momentum before, and since those momentum are equal, you can put them either side of the equation, and you have you can then solve for what the momentum of that third mass is. Okay? In a diagrammatic sense, you begin on the right-hand side here with the problem, and you want to end up with the solution on the right-hand side. So the problem is usually either a scalar or a vector. And if it's a vector, it's usually a property law, and if it's a scalar, it's a mass or charge, that kind of thing, or electric charge. And each one of these has got associated analysis tools. This would typically be a free body diagram, and that might be a control volume or one of the electrical laws of nodes and voltage loops and the node problem. And then you have to, once you've sort of analyzed the problem and understand the problem, then you can look at the various mathematical forms and the equations that you may have, that are pertinent from here, and how to put them together, and that will get you the solution. Now, planning backwards, you know the solution is a force, therefore it's going to be up through this path through here. And then you look at the givens, and then you can sort of work it through. So you've got to, first thing is to decide whether it's a vector or scalar. Sketch a diagram, that's often given. Select the most appropriate analysis tool. Again, it's usually fairly straightforward. Establish a coordinate system. That's not a trivial matter, so it's a convenient one for the problem. Then resolve the various vectors if that's part of the solution. What's constant in the parameter, in the problem? What parameter? Is it the velocity, the energy, the momentum? Select those pertinent equations, and then beginning with the overall system equation, and then work backwards from the desired solution. So you can work back and forth here to usually come up with a pretty good solution of how to lay out what the solution will be when you evaluate it. By physics field, certainly when you're the first semester of physics at the college level, it's primarily just the mechanical line here, and you have vectors and scalars. The electrical area is the next one in the second semester, and then there may be some scalar, thermal, and chemical or nuclear. Those tend to be all scalar properties generally, and involve mass, energy, and charge. Thermal is a scalar problem, okay? So the mechanical vector forces and moments, they can be applied or generated by mass in a gravitational field, friction, etc. The electrical forces and moments between charges in a field, or as it goes through here, you can read through it. And interestingly enough, and this is what makes the second semester of physics more difficult, is that the vector fields are used in electricity and fluid mechanics in more advanced courses in fluid mechanics. Okay? There's a sort of 4 parts to solving the problem: physical diagram, a free body diagram, if it happens to be a vector one, an analytical description of the problem in terms of equations, and coordinate systems. Again, you can go back and read this later, and then you execute the thing either by simultaneous solution or serial substitution, and you put it together. And again, there's just additional consequences of each one of these pieces in the lower lines. Okay, so the sort of strategy is analysis and synthesis, and I'm sort of talking about the analysis is involved with understanding the problem and separating the givens from the desired. Oftentimes, because the problem is written so concisely, it's difficult to sort of extract that when you read the problem quickly for the first time. One way to separate them might be to underline what the desired parts of what the equation is that is desired in the text, and that might simplify the problem statement. Another way would be to look at the answers if it's a multiple choice question, and what are the units of the final answer? Is it force? Is it moments? Is it energy? That sort of thing. The synthesis then is you've got to recognize there's 2 parts to this to do the solution, which is these tasks. You've got to plan the solution, and then you've got to numerically evaluate it. The tactic is to look and find or discover the linking condition, the variable, and it's often not stated, but it's implied, as I mentioned earlier, like the momentum of a stationary system stays constant and zero. And it is that in the sense that they're oftentimes testing you on is this higher level condition, your ability to recognize that in the problem. Another thing is to sort of construct a table of the various values for the states before and after, and of course a degree of for each one of the degrees of freedom. Like in a vector, it has an x and a y components, so you'll have those are degrees of freedom, and so you'll have various values for that. Again, that sort of thing might help you to unwrap the problem state. So what's typically not stressed enough is the fact that you do have these conditions or states at a problem at time 1 or time 2, or what if we do this. Differences have meaning. x2 minus x1, which are positions along the coordinate axis, is equal to the length. And it equals x if x1 is equal to 0, which is the origin or the reference. The relationships between the states is the property law or the principle of the conservation of energy. The center of gravity, which is a concept, is very useful for free body diagram analyses, where you consider the geometry of the body rigid with the center of gravity at the geometric center of the body. This is assuming the mass distribution is uniform, which it usually is in these freshman physics course. Here's just 10 steps. And again, there's nothing particularly new about what I've mentioned here. It just kind of gives you a numerical stepping through the problem if you want to come back and look at that. Okay? Now, the real thing here is these mathematical forms that you have. And the very idea that you have these different forms is useful to think about in terms of how you're going to design or generate the solution. You can either have one equation and use it once, or you can use it twice, therefore it's the same here. It oftentimes would be could be a property evaluation like F equals ma, and you just use that, or a conservation of mass, or energy, and momentum, these various equations, or in this, as we've said in earlier view graphs, rules which are special cases. And you could use the same equation twice if they wanted a ratio of forces, for instance. What if we doubled the mass? And I'll show there's an example of that here coming up. Or you can have two different equations with one unknown or two unknowns. And if it's just one unknown, you'll just have a serial substitution. And again, I have an example of that. Or an equation of two ways of stating equivalence of force, and then you just equate the forces. Or you could have a vector solution, 2 coordinates, which would be 2 unknowns. Okay? So here is some examples of the one equation once. That's the single step, F equals ma. Two equations, one equation twice, where you have the ratio of the accelerations when the mass is doubled, for instance. Two equations, one unknown. What's the weight of the block? A block of iron. You got the density, you got the volume, and then you have to combine them, and then you work down through here. Or you have two equations and two unknowns, which is a sort of vector equation in which you have to solve the x and y axes independently, or a simultaneous solution of equations where the variables are defined by values in the equations, and the variables are dependent on the value of the other one, of the other value. For instance, the river problem of a boat on a river going upstream and downstream. Okay. Problems can be stated for two different states, old or new, state 1 or state 2, or at one state and the process between these states. So that's the sort of situation. They can be nominally the same for each state or condition, but the values of the conditions that are given are different, and therefore you get different equations. Equations for principles usually involve the sum of the terms. Energy conservation equation is equal to 0. The special case rule of the momentum equations is a constant value before and after, because there's no external force or moment. Okay? And again, that's discussed in the first lecture, or the second lecture. Equations for property laws, a combination of terms, force equals mass times acceleration, or ideal gas. Again, there's those sorts of equations. And the idea, of course, is to convert the problem statement into these various equations and combine them appropriately, solve for the desired answer, and realizing that in vector equations, which you can write down in vector equations, the vector notation involves a series of operations, which is a subset of the mathematical conventions and practices that you would use to solve vector equations. Okay? Scalar problems, you have again through here, I've talked about the states or the conditions and the values that those particular things give the differences. And oftentimes there will be a thing in which they want an equivalent combination, a resultant of a combination of vectors. Or you have devices that are combined in series or in parallel, like one spring and then another spring, and then what's the overall elastic stiffness, or how far did it extend if a certain force is put on it. Or the strings are in parallel and they're connected together, and then you pull them apart. And similarly in the electrical, they have the equivalent kinds of things in the electrical material for capacitors, resistors, and inductors, combining them as a unit. And that's useful to combine them for solving various circuit problems. Okay? Now, in terms of some ideas on studying and taking exams, I know this may come as a shock, but the lecture should not be the first time you've seen the material. You see the material. You should have read the chapter backwards from the summary. Review the summary material, and then sort of read backwards in a sort of skimming manner the material that you see in the summary, and so then you'll know what is it actually applying to when you see it. Oftentimes, the summary will end up with an equation, which is what you're going to be given on the exam, but there'll be a derivation in the chapter. You don't really need to remember the derivation, just generally how it was done and what the conditions were and assumptions that were used to derive it. You should look at the example problems, but again, look at them backwards from the desired, and how did they get to the desired, by diagramming the solution. And again, I'll show you here in a minute what that would look like. Print out the lecture PowerPoints and study them. And then bring the PowerPoints to the lecture and make the notation on the slides in their margins as the professor is going through it. This avoids you having to actually spend time writing out the equations that the professor is giving, as he's writing them on the blackboard or oftentimes in his PowerPoints. And so you can then just get the important pieces on there, and so you're going to be making notations about his assumptions or why he's doing such and such a thing, which you wouldn't necessarily put down if it was you just had a blank sheet of paper to begin with. So it's that sort of preparation, along with doing the homework problems, how you should spend the 2 hours of outside study per lecture. That's what's recommended, and you do what I've just said above. There's plenty of time, and it'll take you 2 hours to do it, especially the homework problems. Don't just do the homework problems. Do those after you prepared for the upcoming lecture. Also, you should do the homework with a few students so that you avoid getting stuck and wasting time. Now, if it's required that you have to do them on your own to get credit, that's what I don't know whether you can do it or not. It might be unethical to be doing it. But the best way to learn this material is with a few students, so that you're explaining it to each other of what and why you're doing it. And certainly it's likely you're less likely to get stuck if there's a couple of brains on the job at the same time. Work the exam problems, the worked ones, by diagramming the solution, and so that you can then study the solution, understand the strategy. So this is what I'm trying to do here in these lectures, is to try to get you to think above the problem. How is it gone about and doing it, rather than the details of the numbers. because the numbers are numbers. And you want to avoid just getting lost in the numbers. So here's a sort of diagram of the solution. You'd be given these sorts of values here in the problem, and you would be desired the force, for instance. And and you don't know what the force is at the moment. You don't know what it is, but you know that if you're going to have the force, you've got to have an equation that has force in it. So here's an equation that has force in it. You don't know what the mass and the acceleration are because it's not given up here. So, but we can get the mass by using a few of these terms up here, some of these variables, and again you can get the acceleration by the various values of the variables given above. So once you've sort of worked that out, which is a diagram of the solution, you can then just put the numbers in and work it through. And of course you have to put the appropriate units down here. Okay? So that can be a very powerful way, and once you've got that and you take an example problem and circle the various pieces, you can see how the problem is solved, and you see the general flow path through it. If there's another layer in here, you can see how it might be difficult to see right the way through to the end, and that's what the problem is. Whereas if you sort of plan it backwards, you may be able to work through that, because you know it's got to be in terms of the variable that are given. And there's not another variable out here that you can bring in. So if you've got all the variables and you've got this answer, then there's probably only going to be one path on how you can work that through. Okay? So you recognize that there's different knowledge types. There's content structure, and the structure of that, hierarchy of the various concepts, principles, properties, and the various rules. And again, that's from the previous lectures. The process structure, there's a hierarchy of steps in the procedure. Recognize the distinction of those knowledge types and the various values in your mind, the thinking activities of analysis and evaluation. Plan backwards, work or execute in the forward direction. Study the material many times before an exam. Read it backward, so that and then when you're reading it for understanding, you'll understand what you don't, you'll understand what is being said and where it's going. And then taking work examples in your textbook or other examples online or in other textbooks, and diagram those solutions backward from the answer. Various test taking, since there's labs, which they're graded or not, you should work in teams. Be prepared so that you can become the team leader, and then you can teach others. That's perhaps the fastest way to really, if you can explain it to someone else, then you probably know it pretty well. Homework, work in teams of 2 or 3, so you don't lose time when you get stuck. And exams, like I said, diagram the worked problems backwards, and see the solution structure, and see how the problem is set up from the problem statement. How did they get to that sort of solution structure? Okay? So again, backwards, use a full sheet of paper on homework, diagram the solutions of examples, and the ones you work, so it makes a neat and clear solution diagram. Redraw if it's not so. Again, this perhaps may not apply to the physics problems, but it's good practice to get into this, because when you get into the engineering problems, they get to be more complex, and you have to think about diagramming them and drawing them out sometimes. And partial credit becomes the norm there. Separate the stapled sheets of paper and then restaple them afterwards. Read through the exam and mark the problems you can do, and do those first. So allot the time that you spend on a problem to the worth of the problem. Oftentimes on multiple choice exams, the physics exams are that type, all the problems are of the same worth. So then it's just a question of doing the ones you can do that you have the most confidence in, and doing those first. If there's partial credit given, which it will be in engineering courses or physics courses later on, you've got to show how you set the problem up, the various tools, the diagrams, the various states, process. And if you do a solution diagram, it'll help the instructor or the professor understand your thought process, rather than having to construct it from a jumble of stuff in which the solution was here, 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 and all around on the page. It'll give her partial credit, so you could Even though it's jumbled on the page, you could say here, and then I got this piece, and then I got that piece, that sort of thing, to the various variables. I've had to grade problems in thermodynamics, fluid mechanics, courses like that. And and you're trying to give as much partial credit as you can, but without a diagram, it's hard to know what the student was actually thinking. Okay? So here's a sort of counterintuitive observation, that the more you learn, the slower the problem solution process will likely to go as it starts. This is because you will realize at how many points you can make a mistake, and so you'll slow down and you think, oh, is it a positive or a negative, until you'll question your solution process. This is the way you get past your impatience. So don't be discouraged, and very quickly, if you're thinking about this sort of thing here, you'll get the knack of these, solving these problems and be able to do them relatively quickly. Classifying the solution by the math type rather than the physics problem type should be more beneficial, I think. And learning to plan backward from the objective, it's a skill that you'll use both in the physics courses and in all of the rest of the courses, STEM courses certainly, and even in other classes you can do that, and throughout your career. Okay? So, in terms of what I've concentrated here on is on the procedural knowledge, not the content knowledge or the situation of the problem and the problem types. You're expected to use creativity and judgment to adapt and adjust the knowledge to the particular assignment or the problem. That's what they're testing. So that you shouldn't have memorized these things. That's why the problems are sufficiently difficult. So when you reflect on what you've heard, you should realize that there's two parts: to get an answer, a solution, a plan, and then the execution of that plan. You should, when you think about this thing, you appreciate your problem-solving advantage over other students in your class, because this is a sort of a wisdom approach rather than just being smart, being able to do tricky problems quickly. This is kind of looking at the strategic view of the subject and how to solve the problem. Most instruction expects you to learn by doing and doing and doing, and they don't really give you much guidance. They really won't think about how to tell you how to do this to the extent that this video has attempted to do. So if you tell your friend, it's helpful to tell your friends in other classes in college so they're not at a disadvantage. If you're graded on a curve, then the enlightened ones will have an advantage. So good luck and success in your careers.